Names matter in formal science. A precise name encodes a mathematical claim. It is not a mere marketing descriptor. While much of the standard model relies on terms born from historical accident, the acronyms ODTBT and TWIST serve as foundational blueprints. If the name is accurate, the underlying physical intuition is accurate. The validity of this terminology rests on a measurable metric: 7 years of formal mathematical development and over 4 million computational trajectories. Through this computation, the framework demonstrates a specific capability, deriving quantum particle mass ratios purely from underlying geometric structures. The linguistic constraints of the names define a physical system that scales from the mechanics of quantum particles to macroscopic acoustic resonance. We will deconstruct these 10 letters from first principles, exposing the architecture and mechanism governing the physics. When a physical simulation predicts measurable mass and acoustic geometry without external calibration, the concepts naming the framework function as proven theorems. ODTBT outlines the macro-architecture of the system. The initial primitive of the theory is oscillatory. Notice the difference. The standard model on the right assumes movement is monotonic from state A to B. On the left, a continuous phase field cycles through recurrences, retaining phase memory. The physical state is a repeating geometric pattern, not an isolated event. The D stands for dynamics. This specifies the central point of departure from conventional field theory. The conventional approach on the right treats the vacuum as a fixed background. On the left, ODTBT requires a dynamical background, driving phase flows and basin evolution. Stable physical structures like escape corridors or nodal lines are the emergent residue of these active background dynamics. Therefore, observable particle mass ratios are not injected into the math as fixed variables. They emerge from the movement of the dynamical background. Recognizing the vacuum as an intrinsically active structure removes the requirement for external forces to drive quantum interactions. The first T is transductive. It is an adjective describing a native property of the system, not an external process applied to it. The system converts phase momentum into mechanical momentum and field energy into basin geometry as an intrinsic property of its own structure. This diagram displays what bridging connects. It formalizes a link across 4 scales: quantum particle mass ratios, computational basin dynamics, acoustic Chladni patterns, and engineering plasma confinement. A continuous mathematical correspondence line drives through the hierarchy. The identical geometric equations govern all 4 distinct domains. The final T is theorem. A theorem relies on derivable consequences, distinguishing it from models constructed on fitted data or engineered assumptions. The specific lambda equals 0.22 resonance condition was never manually coded into the mathematics. It emerged as a necessary structural consequence of the geometry. Transductive bridging establishes a mathematical chain where macroscopic physical observables are derived directly from hidden quantum coherence fields. While ODTBT maps the macroarchitecture, TWIST defines the micromechanical action executing within that framework. The T represents threshold. This identifies a specific critical crossing point, distinguishing it from a continuous, smooth gradient. Physics manifests these thresholds. The lambda equals 0.22 capture feature and the nuclear Coulomb barrier operate as dividing lines. This illustrates waveform. Left, standard mechanics features a singular point mass bouncing off a barrier. Right, a distributed phase waveform encounters the threshold, triggering distinct node reactions. 2 waveforms with identical total energy trigger entirely different interactions if their internal phase distributions differ. Standard quantum tunneling models only measure average energy and ignore structural distribution. TWIST addresses this blind spot. Accurately mapping physical outcomes at a boundary requires computing the internal geometric topology of the waveform itself. The I is interface. A threshold exists as a 2-dimensional surface area, never occupying a 3-dimensional volumetric space. This interface manifests physically as the critical shells in computational basin mapping, and visibly as the nodal lines on acoustic Chladni plates. The S stands for state. In this framework, state is a discrete binary classification. A trajectory is captured or escaped, locked or unlocked. Finally, T is transformation. Distinct from simple evolution over time, a transformation alters the spatial organization of the system while preserving its mass and identity. We observe this in a laboratory cymatics analog. A chaotic distribution of fine sand vibrates randomly, then snaps into a locked, symmetrical standing wave. This maps back to the quantum reality. Physical mass is conserved at the interface, while its geometric interpretation transforms. TWIST isolates the precise spatial boundary where chaotic motion transduces into observable physical order. The two acronyms synthesize into a complete operative unit. Every measurable result within the ODTBT architecture is driven by a mathematically precise twist event. Earlier iterations of this research referenced a topological bifurcation theorem. While that terminology described the observable outputs of the equations, ODTBT and TWIST describe the operative dynamics causing those outputs. The physical evidence is concrete. A functioning cymatics laboratory produces physical, acoustic analogs that mirror the basin geometries derived from pure mathematics. 10 words established as an initial linguistic intuition have been developed over 7 years of formal mathematical derivation into a predictive model. The framework indicates that when theoretical nomenclature strictly encodes geometric structure, the resulting derivations align with physical observation.